This is Lecture 1E for Calculus 1. It is a lecture on the symmetry and transformations of graphs and functions. I have a note here on symmetry. Symmetry appears in many things, especially those we consider beautiful, such as mathematics and physics. If you happen to study physics, you will see that there is quite a search for symmetry. And when it's found, sometimes it is equated with the truth. But for objects that we'll study here, we're looking for symmetry about a line or symmetry about a point. Okay, the classic example is a snowflake. The snowflake is said to have six-fold symmetry. What that means is that I can draw 6 lines on the snowflake, and the snowflake will appear to be identical on either side of those 6 lines. For example, I could draw this line right through here. And you can see that the snowflake is the same on both sides of that line. We say the snowflake has symmetry with respect to that line. On this figure, ignoring the photographic problems here and a little bit of blur, it does not have any 6-fold symmetry, but it still does have symmetry. I could draw a line right through the middle of it this direction. You can see it's the same on both sides. And there would be another line of symmetry right through the middle. Okay, so those are lines of symmetry. And another mental picture for it is that if you drew the line of symmetry and you took the picture and folded it upon itself, both sides would match up. For functions, or rather equations, we look especially for symmetry about the x-axis and about the y-axis, and symmetry about the origin, that is a point 0, 0. If the equation is symmetric about the x-axis, it is generally not a function. There's only one function that's symmetric about the x-axis, and that would be y equals 0, the line right along the x-axis. Because if you took a graph and you folded it about the x-axis and the two sides were on top of each other, matched up, that would mean you had values, two values of y, so that they could match up. Each value of x would then have 2 or more values of y, and it would by definition not be a function. For symmetry about the y-axis, if the equation is also a function, if the relation is a function, then we call it an even function. If it's symmetric about the origin, then it's called an odd function. There are various algebraic tests for symmetry, and you'll see here, when you look at these algebraic tests, you'll see why symmetry and transformations are put together. The tests for symmetry are the tests for rotation, horizontal and vertical rotation. So for an even function, the test is that we start with some function f of x. We replace x with minus x. If after all the algebra we have exactly the same function back, then that is an even function. Replacing x with minus x rotates the graph about the y-axis. So here's an example. I start with y or f is equal to x to the 4th power. Obviously this is an even power, and that's kind of a hint as to why these are called even functions. I replace x with minus x, and this is an important point here. When I replace x with minus x, I probably have to do it in parentheses. If I just stick the minus sign on the outside, that is not equivalent to replacing x with minus x. Now I can work out the algebra and see that I get back exactly the same function I started with. Therefore, this is an even function. Now for the odd function, I'm looking for symmetry about the origin. I apply exactly the same test. I take x and I replace it with minus x. After all the algebra, if I end up with the negative of the function that I started with, then it is an odd function. Here's an example. I'll start with x to the 5th, an odd power, which again gives a hint as to why it's called odd. I'll replace x with minus x, again doing it in parentheses because I'm replacing the x with minus x. X to the 5th, odd power, you'll still have one negative sign left over. We end up with a negative of what we started with. Therefore, this is an odd function. The transformations are grouped as vertical transformations and horizontal transformations. The vertical transformations are intuitive. The horizontal transformations are counterintuitive. Okay, for a vertical transformation, if I want to move a graph up by 3, I add 3 to it. If I want to take that graph and shift it down by 5, I subtract 5. The horizontal, it's the other way. You think if you added 3, you would go to the right where there are positive numbers, and that is not the case. there's a difference too in how you modify. When you make a vertical transformation, you modify the function. For horizontal transformation, you modify every occurrence of the independent variable. So here are two examples. I'm using exactly the same function, x squared minus 14x plus the sine of 3x plus 7. Okay, I'm going to make the vertical modification of rotating this function, rotating the graph about the x-axis. To do that, I multiply the entire function by minus 1. So you'll see here I put the function in brackets, put the minus 1 on the outside. Now you can go ahead and do the algebra. That would make a vertical modification. For the horizontal modification, I'll be rotating the function about the y-axis. To do that, I have to modify all of the x's. So here's an x squared. I have to, again, using parentheses, probably said that enough, I'd have to put minus x squared in parentheses. Okay, this x here turns into a minus x. The x that's buried in the argument of sine becomes a minus x over here. When I work out the algebra, this is what I get. The graph of this function would rotate about the y-axis. Here are examples using the function x cubed plus 1. I want to rotate about the x-axis, rotating about this axis. So I started with x cubed plus 1. To do this vertical modification, this vertical rotation, I multiply the whole thing by minus 1, and you can see the red line turns into the dashed blue line. It is rotated about the x-axis. Here's the horizontal rotation of exactly the same function. Again, I'm starting with x cubed plus 1, and then I change the x into negative, minus x cubed with a minus x in parentheses, and you see that this red graph now rotates about the y-axis. Vertical stretch and shrink is another kind of vertical transformation, and again, it is intuitive. I have a function. I'll start here with y equals the square root of x. Okay, if I multiply the entire function by 3, that means I'm going to end up with 3x to the 1/2. Then the point that was here at 1, 1 now moves up here to the point 1, 3. It's as though I took the function and just stretched it up. If I had negative values, those would stretch down. Okay. If I take the same function and I multiply by a number less than 1, I multiply by a third, then the point that was here again at 1, 1 now becomes 1, and the y value is 1/3. So the graph, the blue line, got compressed towards the x-axis. So for vertical stretch, the graph is stretched away from the x-axis. For vertical compression, the graph is compressed towards the x-axis, and you do that by multiplying by a number greater than 1 to get stretch, less than 1 to get the compression. Now I'm going to do the same thing for the horizontal stretch and shrink, and you'll see that it doesn't work the way you think it should. So I start with exactly the same function, y equals the square root of x. If I modify the x so that it is multiplied by a number greater than 1, then this graph, the blue line, gets compressed towards the y-axis. The point here that was 1, 1 before now becomes 1/3 1. 1/3 for the x, y, and the y value is 1. Why is that? Okay. To get the y of 1 for the original function right here, x was 1. If I want the value of 1 again, what does x have to be? It has to be 1/3. And that is why it's compressed towards the y-axis. On the other hand, if I multiply the x, again using those parentheses, by 1/3, 0.33, then the point that was at 1, 1 is now at the point 3, 1, because in order for y to be 1, x had to be 3. So that's your horizontal stretch or shrink. For horizontal stretch or shrink, you're stretching away from the y-axis or compressing into the y-axis. For all of these translations, the horizontal translation is probably the one you're going to use the most. It is very counterintuitive, but it is very important. It's especially important in timing switches in electrical engineering. I'm going to start here with just this parabola, y equals x squared. Now, because it's horizontal, I modified the independent variable. That will be x. So I have subtracted 3 from the x-axis. You would think you would move to the left. No, you move to the right. If I add 3, now I shift to the left. What is the reason for that? Look again at a point that's pretty easy to identify. That's this 0, 0 point right here at the origin. On the original parabola, when x was 0, y was 0. Now over here, what did it take to make y 0? X had to be a positive 3. What does it take for y to be 0 on the green one? X has to be minus 3. So that is the counterintuitive behavior of horizontal translations. So if you have a switch that was set to go off at time t equals 0 and you want it to go off 2 seconds later, the equation then would have terms like t minus 2 in it. The minus 2 would move that time 2 seconds later.